Hello everyone! There are many videos about reinforcement learning out there, but I want to do something different in this video. First of all, I'm going to explain how psychology and animal research inspired the creation of reinforcement learning. This will set you up to understand the intuition of deep cue learning. By the end of this video, you should understand reinforcement learning jargons such as agent, action, reward, and state. I will explain what is gamma, the discount factor, as well as cue learning and policy. And finally, we will derive the Bellman equation together, which is also the cue loss function. So let's begin. According to Richard Sutton, who is one of the founding fathers of reinforcement learning, the development of reinforcement learning was inspired by a classical conditioning model called the Rescorla-Wagner model. Rescorla and Wagner were two Yale psychologists who studied classical conditioning and reinforcement with animals. They presented a famous finding that animals, including humans, only learn when they are surprised. So what does this mean? Let's say we have a bunny. The bunny has access to a button, and the bunny currently has a low opinion of the button. He has never had any interactions with it and thinks that it's useless. Mathematically, this means that he believes the reward associated with pushing the button is 0 at the current time t. One day, the bunny accidentally pushes the button. Maybe it's a random act of exploration. And he gets a reward, a strawberry. The bunny is very surprised, and he updates his belief about pushing the button that it's actually an action that's valuable. He learned from this experience that the reward from pushing the button is a strawberry. So by being surprised, he learned something new. And surprise triggers learning. Let's say from now on, the bunny keeps on pushing the button and he consistently gets a reward. The classical conditioning is now established. The bunny knows that if I push, I get a reward, and there is no surprise. The reward function is still correct, and there is no need to update it. And this is the idea that when there is no surprise, no learning has occurred. Until one day, the bunny pushes the button, and there is no reward. The bunny is again surprised and updates the reward function that sometimes by pushing the button, the reward is nothing. Alternatively, if he pushes the button and he gets 2 strawberries, he would also update his reward function. And this is the idea that animals, including us, only learn when we are surprised. It is also the idea behind the Bellman equation, which we will cover shortly. Now, let's draw the connection between the bunny and reinforcement learning. We have an agent who observes the state of the world at time t. The agent takes an action which causes the environment to output a reward, and the state of the world is now different because of the action. We can also take a look at another example. Let's think about stock trading. We have a trader who observes the state of the world, and it could be the current prices of all kinds of investments. The trader executes an action which could be trading a stock. And now the environment has changed because of his action. By trading a stock, he has changed the current price of the stock, so the state of the world needs to be updated. After seeing the result of his action, if the result is surprising, such as you made more or lost more money than expected, the agent learns a lesson and updates the cue loss function. I will explain the cue loss function very soon. And this process repeats in a circle continuously. By taking actions and interacting with the world, we get rewarded or punished. And if these results are surprising, we learn lessons from it. And these lessons will in turn change the actions that we take in the future. Rewards is an important concept in reinforcement learning because rewards guide our actions. They shape how we learn. If an action is rewarding, we learn to do it more often. Rewards can also take on negative values. If we are punished because of an action, we learn to avoid it in the future. In a bunny example, the total reward is just the strawberry, and that's the end of the story. But in real life, an action can have far-reaching consequences for years to come. For example, the decision to drive home while being drunk may lead to an accident that impacts the rest of someone's life. And you can think of the total reward as the sum of all the rewards you're going to receive in the future as the consequence of taking a specific action. Think of it as if you bought a stock and hold it forever, you're going to receive dividends from it over time. But how do we know what's going to happen in the future? It sounds ambitious that we want to find the ultimate reward of an action over an infinite amount of time, given that none of us can live forever. We don't know whether the company will continue to give dividends or if it's going to bankrupt some point in the future. The solution of this problem lies in the Bellman equation, which we will cover very soon. But for now, we need to understand the discounted total reward. We add the discount factor, gamma, into the equation. Empirically, gamma is usually set to a number like 0.9. So it's going to look like this. This means that the future reward is discounted. The gamma is there to show that the future is uncertain. We're not very confident about what's going to happen. And the further we go into the future, the more we're going to discount the rewards because we can't be sure about what's going to happen. And the current reward is not discounted because it's to the power of 0, so we can pretend gamma is not there. Another benefit of having gamma is that we can make sure this reward sequence is going to end. When we let the sequence go on forever, eventually we're going to have 0.9 to the power of a very large number, like 0.9 to the power of 1000, and that's essentially going to equal 0. This practically ends the sequence. This way, we don't need to wait an infinite amount of time to see what kind of rewards we're going to receive in the future. To summarize, when we evaluate an action, we consider both the short-term and long-term consequences of the action. The future reward is discounted by adding the gamma discount factor. We take the short-term rewards more seriously because the future is uncertain. We can't delay gratification forever, and there needs to be some short-term benefits to keep us going. Now, what is Q learning? You already know about the discounted total rewards. It is the discounted sum of all rewards as the consequence of an action over an infinite amount of time. And here is the Q function. Q stands for quality. It captures the quality of an action. And Q is the statistical expectation of the discounted total reward. But how is Q different from the rewards? The difference is that Q considers the action space. In the real world, we always have many options. The bunny can choose to push the button or choose not to push the button. And similarly, a Wall Street high-frequency trader has hundreds of stocks to choose from. They can buy a stock or sell a stock or do nothing. Let's say the probability that the bunny is going to push the button is 0.9, and the probability that it's not going to push the button is 0.1. Then Q is going to equal the rewards you get for pushing the button times 0.9, plus the rewards for doing nothing times 0.1. Once we have the Q function, it is easy to take actions because we now have a formula for how to make decisions. We need to understand a new concept that is policy. The agent uses the policy to infer the best action to take as state S. The policy is very greedy. It's going to tell the agent to exploit the action that maximizes the reward from the Q function. In reality, we don't want to be so greedy. We want to balance exploitation with exploration. For instance, if I only order my favorite dish from the restaurant 100% of the time, and I don't ever try anything else, I will never know if there's something better. So in reinforcement learning, the agent sometimes deviate from the current best action and try different actions randomly just to see if there is something better out there. So it might do something like this. 50% of the time try the favorite dish, but the other 50% of the time try something else. Now, let's get back to the thorny question of how to compute Q and the discounted total rewards. Assuming we always take the action to maximize Q, we have the current reward, which is just RT. The next reward is going to be discounted, which is why we have gamma, the discount factor here. The Q function is going to return the total reward given that the agent takes the action that's going to maximize the reward in the next state of the environment. The total discounted reward is simply the current reward plus the next reward. Notice that this is the same thing that we covered before. The total discounted reward is the sum of all the rewards we're going to receive over time as the consequence of a single action. Next, let's bring back the Q function, which is the expected reward at time t. Let's say the Q function is powerful and it encapsulates all the rewards that would come from the future because of a single action and is correct. Then ideally, the Q function will equal the total discounted reward. This relationship is really important. It's key to how we can solve the problem. Now let's try to understand this equation. Think of the left-hand side as the agent saying, I predict this is what's going to happen from day 1 until the end of time. And this is the same thing as the long string of rewards that we saw before. Now think of the right-hand side as what already happened on day 1, plus the agent saying, I predict this is what's going to happen from day 2 until the end of time. This is also the same thing as what we saw before. So overall, this equation conveys the idea that in a perfect world, if the reinforcement learning agent understands the action perfectly, meaning that it can predict all the rewards that will be gained because of an action, then there is no surprise. Because if you know exactly what's going to happen, you wouldn't be surprised. And the agent wouldn't need to learn because it already has perfect knowledge. But in reality, there is always a gap. The Q function does not perfectly capture the total discounted reward. We don't always know the true value of Q, but we try to approximate it. So the gap is just the difference between the two. The gap captures the idea that animals only learn when they're surprised. In fact, the gap we derived here is the surprise. As long as there is a gap between the prediction from now and the prediction from a step later, the agent needs to keep learning because the prediction needs to be updated. The gap is also part of the Q loss function, and we take the square to get rid of the sign. The Q loss function is trying to minimize the gap, and the Q loss function is extremely smart. Originally, we have to calculate rewards from t plus 1, t plus 2, continuously over an infinite amount of time. We can't possibly observe all of these rewards from the future. But now, the objective becomes simpler. By minimizing the gap between the current state and the next state, we can continue to train the neural network. We only need to observe what happened now and what happened one step later. Through iteration, we turned a complex problem into a simpler problem. The Q loss function is also called the Bellman equation. So there you have it. And this is the basic concept behind reinforcement learning. If you learned anything useful, please hit the like button, and I'll see you next time.